Yeah.
Yeah.
Okay. Hopefully it's not grainy. Okay, so here's the program that we wrote. All it did was, well, define a list of times, define G, define the initial position and velocity, computed the velocity as a function of time for X and Y directions, plotted that, computed the positions as functions of time in the X and Y directions, plotted that, and then plotted X versus Y so that you have a trajectory. Parabolic trajectory, I suppose. And then finally, we did plot it in sequence, in a loop, in a manner that you essentially get a animation. I don't know if people tried running the animation at home to see if it ran smoother than what you could see on the Zoom thing. I suppose Zoom might make it a bit more choppy. So you can take a look at it offline, I guess, as you do the next homework. So let me just run it again. And we shall see what happens. Well, it's actually choppy for me. It's a bit because I think my computer is struggling a bit because it's connected to various things. It's transmitting via Zoom, and it's, I suppose, uploading the video onto the cloud and so on. Anyway, so, but you can, hopefully people can see the animation, okay? Sort of maybe slightly choppy. How does it look? Looks good, Daniela says. Okay, okay, sounds good. Okay, so the very last thing that I did last time, sort of in a hurry, was to add this trail at the very end. So the original version of the program was just plotting X list of iframe and Y list of iframe, which is just that ball flying through the air. And then I added this line. So this is actually adding a trail. So basically it's the trajectory so far. And this is actually the ball. And recall that X list and Y list contain the whole trajectory, and we're just plotting things one at a time. So here we're just plotting the ith frame or the ith X and Y position. And to plot the trail, but just up to the current frame, we are basically doing X list of 1:i frame. So basically taking all the data points, but until the current frame, so that the trail kind of follows the ball. And then when it's done, you've got the whole trajectory, but it doesn't plot the whole trajectory, it just plots the current, until the current frame, I guess, so. Okay, so that's a pretty, and then notice that we did hold on, hold off. This is something that I did end of last lecture. So we're plotting first the ball, and then we are doing hold on so that when we plot the trail, the ball doesn't vanish. So we do plot the trail, and then we make sure that the axes are equal so that 1 unit on the x-axis is the same as 1 unit on the y-axis. And then we are specifying what the range of the x and y axes are based on what the trajectory looks like, I suppose. And then we put a little bit of a pause, roughly 0.01 seconds. And then we use this command called draw now. This is forces MATLAB to draw now as opposed to do things asynchronously. So MATLAB can basically look ahead and sort of anyway, kind of. And then we hold off so that when we draw the ball the next time, you don't have the, it erases the whole thing and then you redraw the whole thing. So that's the procedure. You do hold on, draw everything that you want to draw, and then hold off. and then redo that over and over again. Any questions about this? Okay, if things are pretty clear. So I will do, the rest of today's lecture is going to be solving differential equations in MATLAB. So I'll probably do that today. And then we'll maybe have like a very short 20-minute MATLAB lecture later in the semester. But today will be, so as last time and today will be the sort of main two MATLAB lectures, and then maybe we'll do 20 more minutes or half an hour at some point to do even more complex problems. But today we'll do one simple problem. But then you will see that you can basically use the same method to do pretty complicated problems with lots of things moving around, sort of complex dynamics, using basically the same method. The method is pretty simple, right? So let me see if I can use my iPad to sketch things out before we start. Okay, supposedly this is how I use my iPad, at least one way to use my iPad. Okay, so how does one solve differential equations in MATLAB? Well, first of all, let's say something. All dynamics equations, so to speak, derive from quote unquote sum of forces equals ma, are differential equations. Okay, so specifically, they are ordinary differential equations. Okay, sometimes contracted to ODEs. And they are specifically, well, second order ODEs. Why are they second order ODEs?
Space and time.
Well, there is space and time, but the second order refers to something else.
Because acceleration is the second derivative.
That's right. So that's the main sort of reason. So we basically have, let's say, mx double dot equals, well, sum of all forces. The fact that this is second derivative means that it's called a second order ODE. Okay. Okay, so let's see how to solve this differential equation. Well, before that, well, let's say how to solve this. Have you guys learned of methods to solve differential equations on a computer?
I have personally not, no.
Okay, so there's at least one person that hasn't. So it may be that you will learn it in your numerical methods class soon, or maybe in some other class. Okay, so the simplest method, so of course you do analytical stuff, analytical methods, which you learn in your, I guess, various ODE classes. These are what sometimes called closed form solutions sometimes, by which we mean basically pencil and paper, like analytical solutions. So that's sort of method number one, and usually applies only to simple problems. Like one object moving, things like that. if there are multiple objects sort of coupled together in some complicated way, these analytical methods are basically not useful. And of course, real engineering problems, we often have lots of objects interacting in complex ways. When I say one object, one degree of freedom. Anyway, so there's also some more complex problems that it can address, but we'll skip over that for now. And then we have what are called numerical methods. Okay. Numerical methods are basically using a computer. Is what we mean by numerical methods here. Well, you can do the numerical methods using pencil and paper as well, but that's not the most efficient way to use these so-called numerical methods. Really, you want to use a computer. And there are lots, there are, I don't know, I want to say 1,000 books on how to solve ordinary differential equations using a computer. And there's literally 1,000 different methods of solving, thousands of books and methods, let's say, on this, just this topic. Because it's a big field, and in some sense, all of practical engineering relies on our being able to solve these differential equations accurately and so on, okay? So there's a big field, numerical methods, because without these, we can't really do any real sort of, well, we can do some simple classical engineering, but it's hard to do more complicated things. Okay, so we will discuss something called Euler's method, which is the simplest method. In your numerical methods class, so we will do this. In your numerical methods class, you will see probably this other method called Runge-Kutta. This is more advanced. You may see in your numerical methods class, let me say. So I will not do this. Like I could teach a whole course on these topics, but what we will do is just get a flavor of how to solve differential equations using Euler's method, the simplest sort of thing. So if you were forced to solve a differential equation using a computer, probably after I don't know, a few minutes or a few hours of thinking, you would probably come up with this method. It's sort of the most intuitive thing. So I guess a couple of 100 years ago, no one had thought of this method. So Euler got credit for it, but you could have come up with it, okay? As you will see in a minute. But so we're not going to do Runge-Kutta method because, well, this course is not necessarily about solving differential equations, but I do want to give you sort of a flavor of how these things work and sort of couple that to sort of visualization, animation, and so on. So that's my motivation here. So what's Euler's method? Someone says we do almost everything in numerical methods by hand. Okay, so we'll leave that aside. Yes. Okay, so Euler's method. This is called Euler's method. Okay, so even though these things are, these are second order differential equations, let's first discuss Euler's method for first order differential equations, okay? Let's first do first order ODEs because we do simple things first. But then it turns out that the same method essentially applies whether it's a first order ODE or a second order ODE or 200th order ODE, or if you have one differential equation or 200 differential equations, it's the same method. So starting with first order is a good place to start because the same thing works for anything. Okay, so first order ODE is going to look like this. Let's say, let me just sort of take this example. Let's say dx by dt equals v of t or something. Let's say someone has given you the velocity as a function of time, and you're trying to find the position as a function of time. Find x of t given v of t and x of 0, okay? So of course, we can solve this particular differential equation with analytical methods, like you can just go x equals integral v of t, but we want to sort of demonstrate this method on the simple system. And then we'll see that even in cases where we cannot do a simple integration, this will work, okay? So do people have guesses, if you haven't seen it before, how you would solve this system using a computer? Okay, let me say this thing. So basically, you do this. You say dx equals dx equals v of t dt. Okay, so you just rearrange this thing. That's all we have done. What does this mean? It means a small increment, the change in position x equals the current velocity v times the time increment dt, okay? So if you wait for a little bit of time, the distance by which you have moved is going to be velocity times dt. That's all. Seems like the most natural thing you would say. The current velocity is something. If you wait for a small enough time, the change in position is going to be velocity times time, okay? If you wait for a long period of time, then you have to do a formal integration. But if you wait for a small enough period of time, the current velocity will tell you more or less how much the position changes, okay? So that's all there is to it. And you now, instead of differentials, you write it as delta x equals v delta t. So this is the basic principle. And basically you say initial condition, x of 0 is given, let's say, okay? And then say pick small delta t equals, let's say some really small amount of time, 0.001 seconds. It's quote unquote small. And then we say x at time 0.0001 equals x at time t equal to 0 plus v at time t equal to 0 times delta t, which is of course 0.0001, okay? And then you say x at 0. The next time instant equals x at 0.0001 plus v at the previous time, like at this time instant, times delta t, which is still 0.001, so on and so forth. So in this manner, you can just sort of keep updating x, and you'll basically get x as a function of time because we are just stepping forward in time. So this is called, this you would say, stepping forward in time, okay? To get x of t, basically you're stepping forward in increments of delta t equals 0.0001 seconds, okay? That's what you're doing. And you get x of t, that's it. That's very simple. Then this really simple thing is called Euler's method. We'll see, well, very briefly, we'll see pros and cons of this method. because of its simplicity, it's not the most efficient. It's a bit slow, and it's not the most accurate. But for many problems, it's actually pretty good. So you can at least get started. So instead of writing it in this sort of cumbersome manner, we can write it like x of like some I times delta t equals x at, or let's say k. Well, maybe I shouldn't use k. Should we use I? All right, let's say I. X of I minus 1 times delta t, the previous time step, plus v of I minus 1 times delta t times delta t. Okay, does that make sense? This is basically I times, like if you've taken n steps, it's going to be I times 0.0001. This is I minus 1 times 0.001. That's the time instant, and so on. So this is the actual time. Sometimes people, to simplify, I think I misspelled it. Oops. You might say something like x list of I equals x list of I minus 1 plus v. Let's say v is being computed as a list as well, times delta t, okay? This is basically Euler's method. Does this make sense? The current x is the previous x plus the previous velocity times the time increment. Any questions? Okay, where you're basically saying x list of I is basically your x of t, where t is equal to I times delta t, okay? So at this time is your ith element of x, okay? So that's for, this is for first order ODEs. Okay, so what if we have second order ODEs? Okay, so an example second order ODE is going to be, well, mx double dot equals, let's say f of t or something, just to keep it very simple. But it doesn't matter what the right-hand side is. It could be like some more complicated thing. This is basically MA equals f of t, right? This is all it is. And of course we have so we have basically A of t equals f of t by m. So we of course have dv by dt equals A of t, or basically A. So we can integrate this. We can integrate this to get, let me see what people are saying on the chat window. This is just an approximation, right? Exactly. This is an approximation. So we'll talk about that in a moment. So actually, let's talk about that very briefly right now. When you are doing something like this, you're saying delta x equals v of t times delta t. What is the kind of approximation you're using? What are we doing there? Is this exactly true? So this is actually, oops. This is actually not exactly true. This is just approximately true because really you have to do an integration to get the change in position. If delta t is finite, you have to do an integration. And And yeah, so you can think of it as Ian says, it's like sort of like doing a Riemann sum with very small intervals. It's similar to that, exactly. Yeah. Or you can think of it as sort of a Taylor series approximation, where you're taking out the linear term, kind of. So you can sort of think of it as an approximation in a few different ways. You'll have to do an integral, but you're just doing this delta t multiplication. We can think of it as a truncated Taylor series, a few different ways of thinking of this as an approximation. But absolutely, this is an approximation. And in some sense, the simplest or the crudest approximation. Okay, so you're doing second order ODEs. This is the second order ODE, which is this, which is A equals f of t by m, which is basically saying dv by dt equals A. And clearly we can integrate this to get velocity, right? So we can say, basically you can say, oops. We can say delta v equals A delta t. And similarly, just like before, we have dx by dt equals v, and that gives us delta x equals v delta t. So if you have a second order differential equation and you want, say, position as a function of time, you basically integrate, you update, use both these equations, basically. To update v using A and update x using v. Okay, so that's what we will do. By noting what the acceleration is, you can say, okay, the velocity is going to change a little bit, and you update the velocity. And then by noting what the current velocity is, you can update the position. And you keep doing this, basically. So that's Euler's method if you're given acceleration. So you basically go for I equals 1 to how many our data points, num points. We would basically say v of I equals v of I minus 1 plus A, let's say, of I minus 1 times delta t. And then v of I equals, sorry, x of I equals x of I minus 1 plus v of I minus 1 delta t. And here we may need to compute, here compute A of I minus 1, I guess, okay? That's usually given quantity, which is sort of given. And you sort of put this in a loop, keep doing this, you'll keep updating like velocity as a function of time and position as a function of time. Okay. Any questions? So simple idea. This is also called Euler's method. Of course, you start with like basically your x of 1 is x naught, and v of 1 is v naught or something like that, right? So if you have a list, like here, I mean x list and so on, right? So all this, I've sort of abused the notation a little bit. Here, I mean v equals v list, x equals x list, and so on, okay? I've switched to MATLAB here. If you have, well, lots of particles moving, connected together in some manner moving, so coupled system of many objects. It doesn't matter now. Now that we've seen this, we can extend, we can use the same logic for systems with 20 objects moving together in some complicated way. Let's imagine, for instance, that we have, I don't know, these objects. Let me create some silly thing. Let's say this is a point mass, and then and maybe connected by a spring, another point mass, connected by a spring, another point mass, connected by a spring, another point mass, connected by a spring. Okay, so maybe some system that looks like this. I made it look like a person. Okay, and let's say we have like x1, y1, x2, y2, x3, y3. So these points are denoted by x1, y1, x2, y2, x3, y3, and so on. So you can write differential equations. So you can say x1 double dot, basically a1, ax1 is going to be something, y1 double dot equals going to be something, x2 double dot is going to be something. Usually it's a function of all the other variables, x1, y1, x2, y2. Maybe it's like function of v1, vx1, vx2. It's going to be some very complicated thing on the right-hand side. Complex function of xi, yi, vxi, vyi, etc. It's going to be some complicated differential equation, etc. And you can imagine writing a big system of differential equations, but basically you can solve it like y equals 1 to how many ever num points. And then you would basically go vx1 of I equals vx1 of I minus 1 plus ax1 of I minus 1 times delta t. You basically update each one of these things. Similarly, vy1, same thing, y1. And then if you say x2, so basically for every single variable, you would write a similar equation. And you'll have as many equations as there are degrees of freedom here. And you just set it up and sort of keep chugging along. And you'll, if you know the right-hand side of the differential equation, you can sort of do an animation of this object moving. Okay, so that's how you would simulate a much more complicated system. So let me actually try to do a simple example on MATLAB very, very quickly. And then I suppose we shall stop there. Any questions before we do that? Reasonably clear. So this more complex thing that I just outlined, we will actually do it in the second MATLAB homework, probably not in the first MATLAB homework, but I just gave a preview. We may not do something with 10 points. We may do something with like 2 points or something bouncing off of each other, but still might be interesting, sort of already very complicated looking dynamics, and basically no hope of solving it with pencil and paper. The other thing I want to, and then the first MATLAB homework is probably will stop here, I suppose. The second MATLAB homework, I think we'll probably do like planetary motion or a couple of masses interacting in some interesting way. And so, Rohan asks, does the current X use the previous Vx in its calculation? Usually, yeah, that is the standard way of doing Euler's method. Getting the current X is the previous X plus the previous Vx and then delta t. That's usually the usual Euler's method. Yeah. There is probably not a big loss or difference by using this one, but usually you use the previous one. Yeah. Cool. Let me switch off my iPad thingy and then use my computer instead. And then I'll post my iPad notes, I suppose, on Carbon. as well as the program. Can people still see my screen?
Yeah.
Cool. Cool. Okay. Like I said, for the assignments, it's going to be sort of a low stress thing where we have a nominal deadline of next week. But for this particular homework, because the exams don't necessarily depend on this homework, we are totally happy if you submit it later. But of course, it may be fun to submit it on time. And then if you don't get full points, we ask you to, well, if you want, you can submit it again to get full points, I guess. So it's relatively sort of low stress. And mostly I would like you to have the experience of doing these things because I feel like it's a useful thing to have context for. Okay. Let me close this thing. Save. I suppose I should have kept my iPad on, unfortunately. Okay. Let me just open a new file and I shall do the equations on okay, so we're going to simulate a simple mass spring oscillator, sometimes called a simple harmonic oscillator. Okay. What I wish I had done is perhaps written the equations of motion on the iPad first, on my tablet device first, but we'll just write this right now. So imagine you have a wall, a spring, a mass, okay? And that's all there is. The spring has stiffness mass M, spring stiffness K, spring rest length, namely stress-free length is L naught or something. And really that's it. Mass spring connected to the wall, okay? And you pull it and let it go and then it oscillates. We will add some damping or essentially viscous friction to make it decay as well in a minute. But for now, we just have a wall connected to a spring. Is that sort of clear? Okay. And the equation, if you write F equals ma, basically you have m times a is equal to F, which is going to be basically minus K times position X of the mass times L naught, okay? So X is position of mass from wall equals length of spring, okay? So the mass is a distance X away from the wall, and that distance is basically the length of the spring. So X is the length of the spring, and at any point in time, X minus L naught is going to be the stretch of the spring. And if the spring is stretched, the spring is going to pull on the mass in the opposite direction. So that's a minus K times the stretch, okay? Any questions about this equation? This is basically F spring. That's equal to the restoring force here, okay? So this is the thing that we are going to simulate. So let's do this, use Euler's method. What should we do first? I'm going to do this super fast. Let's see if we can do this in the next 10 minutes, 11 minutes or so. Can people see my screen still okay?
Yep.
Okay. Okay, first we do clear close all CLC. And then what's the next step? I'm going to divide this into modules a little bit. What's the next thing you might want to do here?
Create an array with equally spaced time elements.
We could do that. Okay, so let's do that. So we can say plist equals, let's say, let me just use this version, 0.01. Let's say delta t equals 0.001 or something, just like we had there. And then let's say t duration. Let's make it oscillate for 10 seconds or so. And then basically we create a vector from 0 to t duration in steps of delta t. So we've just done that. This is still a row vector. Let me just make it into a column vector there. Okay, that's good. That's a good start. Let's do another one. I suppose the other thing to do is to define these parameters, k, m, and things like that. So these are the constants of the problem, so to speak. So m, let's say, is 1 kilogram. Let's say k is 1. Let's say L dot is 1, etc. I don't know. Just well, maybe let's make it k equals 10 or something. Anything else? I guess those are the constants. And then what else should we do? So let's do the Euler's method and then and see what we need, and then just sort of iteratively add stuff here depending on what we need. Okay.
The apostrophe there on your T list.
T list. There's an apostrophe here. Yes. That was intentional. This is a row vector. I'm just converting it into a column vector with the apostrophe.
Oh, I see.
Yeah. It just so happens that I like column vectors. The apostrophe does a transpose. And by default, this does a row vector. It totally doesn't matter. It's just my aesthetic preference because the column vector, I can see the whole thing sort of in a linear thing. For a row vector, if I'm looking at it, it sort of goes back and forth and less easy to scroll, I suppose. That's all. Okay, Euler's method. Let's say for let's say I time equals 1, 2. How many points do we have? We can do length of T list, basically. Is it going to be length of T list? Let's write that down and then we'll fix minor errors as we go along. And then we can do something like x of I time equals x of I time minus 1 plus v of I time minus 1 times delta t, something like this. We can call this x list here and the v list here, just to make sure that they're called lists. And then we can do the same thing for velocity, v list, a list, okay? We increment v by using acceleration. Of course, where are we getting the acceleration from? Well, the acceleration is going to be, well, we take this equation here. Let me rewrite that equation right here. Oops. I pressed some weird combination of buttons and it created a red infinity there. Acceleration equals basically minus k times x minus L naught divided by m. That's basically your acceleration here. I'm just rearranging this thing, right? So basically acceleration is going to be minus k. I'm just going to copy this. into here. That's the expression. That's the current acceleration is, or the acceleration at any point in time is the spring constant times, well, x minus L naught. Like, what do we need to put here? What x is this? It's the x at this time, right? Like the force depends on where the mass is at this point in time, so to speak. So basically, this is x list of I time minus 1. So you replace this x with like the current x, so to speak, or whatever. Yeah. Everything else is just a constant. Mass is a constant, L is a constant, K is a constant. And in place of x, you just put in the current x. So you update the acceleration, you update the velocity, you update the position. Will this run?
We start the iterations at 1. There's no 0 index in the
Perfect.
vector.
Okay, cool, awesome. So this will not run because, well, we have not even defined, it doesn't know, for instance, like x list of 0, it's not going to work because vectors are indexed from 1 onwards. So let's actually make this 2, first of all. Okay, so that we are starting from the second element onwards, so that I minus 1 for I equals 2 works out. Like it will be 1, and then x list of 1 will be a well-defined thing. But what is x list of 1? Well, that needs to be provided. So initial conditions needs to be defined. So let's say x naught equals, L naught is 1, which is the rest length of the spring. So let's say x naught is 1.1. So you stretch it a little bit. Similarly, let's say V naught is, let's say 0. So that you're starting initially at rest. You've stretched the spring a little bit from 1 to 1.1. And then we basically say x list of 1 equals x naught, the initial thing. And then V list of 1 equals V naught. Okay, so these are the initial x and V. And then you start updating from the second point onwards. Is this going to work? What did you say? Okay, I couldn't hear. Okay, let's just run it and see. Okay, it ran without an error. So that's nice. So we have V list here. We have X list here. Okay. So these happen to be column vectors because when you update things like this, by default, they're going to be row vectors, unfortunately. So I don't know, maybe I'll just keep them all row vectors or something like that. There are ways to transpose that layer and so on. But okay, so we're almost done here. Let's actually do a figure. We plot T list, comma, X list. And then let's get, hold on. And then we can plot T list, comma, V list. And then we go legend, X, comma, V, if you want. And the next label is time. Let's just run the whole thing. Okay, so that is it. It works pretty well. It's an oscillatory motion. This is x of t. Notice that it oscillates about the position 1, right? So you started out with position 1.1. That is the initial condition. I don't know if people can see it. Hopefully, this is 1. This initial point at time t equal to 0 is 1.1. And you let it go. The velocity initially is 0. This is the velocity curve. This is the position curve. Velocity is initially 0. The position is 1.1. The rest length of the spring is 1. You pull it, let go, thing oscillates about 1. and the velocity oscillates about 0. Okay, any questions? If you had like 3 more minutes, we can actually do an animation. Like you guys know how to do the animation now. You can just move the mass back and forth based on XList. In addition, you can try to connect, like draw a wall. You can try to connect the wall to X with maybe a straight line or something, and actually have like wall, straight line for the spring, and like a mass moving back and forth, and the straight line sort of extending and contracting like a spring would do. And probably sort of do that in the next 5 minutes. But I think we've run out of time, so let me stop there. Actually, let me say one more thing very quickly. We used delta t equals 0.0001. If you actually increase it, you will notice, well, hopefully soon. Okay, something funny happening here. You notice that energy is not, it's actually not oscillating periodically, it's sort of growing in size, this oscillation, which is not physical, right? So it is actually very, very important that this delta t is quite small, needs to be quote unquote small enough, okay? If it's larger than a particular quantity, it turns out that the system will go unstable and do some crazy stuff. Otherwise, oscillations grow, right? So that's the nature of the simplicity of the method. You have to have like a very small delta t so that the system actually gives you something good. Okay, let me stop there. And then I will post this video, I'll post this code. I might actually add an animation as well before I post the code. But this should all be good for doing the first homework, which I will post sometime later today. Okay, so that's the end of today's lecture.